when we felt that we were beginning to build bridges between the mathematicians and the way that they look at things and the engineers who actually got to keep the systems running and the way that they do. And one of the lively people this morning in the audience was Professor Janusz Bielek from the University of Durham. And he's been one of those people who's been one of the early advocates of the need for mathematicians and engineers to work together. And it's very much his vision there that has been part of what is driving this week forward. So he is now going to talk about some of the practical engineering problems, and he is going to talk about, well, you can read as well as I do, wide area blackouts and why they happen. Okay, Janusz.
Okay. Well, thank you very much, Sam, and thank you very much for organizers for inviting me here. So as Stan mentioned, I did some heckling in the morning, so I expect some well-known hecklers who sit over there to do the job. Yes, Mark? However, if the heckling could be constrained to clarifying questions, please, not throwing up discussion, because otherwise we'll never end this presentation. So what I'll be talking about is blackouts. And well, blackouts is an exciting subject to some extent, at least for power engineers like myself, because it's a little bit like in chemistry. The good chemistry experiments are always involve blowing things up, and that in order to keep kids entertained. So this is right after lunch, so everyone is a little bit sleepy. So I thought that perhaps talking about blackouts is about kind of things when things go spectacularly wrong, so this should keep the audience entertained to some extent. So this workshop is about modeling how mathematicians can contribute to understanding how power systems work. So I'll say a few words about modeling, although I'll say more about modeling tomorrow. I'll do overview of some of the recent blackouts and what are the new challenges and how modeling can help in preventing blackouts. And this will involve, quite interestingly, some of discussions which we had this morning in the previous session. So I'll do overview of the blackouts, but what's important, I'll be only talking about so-called wide area blackouts. It means involving there are transmission system-based blackouts. It means this which involve high voltage transmission networks and usually involve millions of people disconnected. However, one should bear in mind that a majority of blackouts in power systems are due to failures in distribution networks. It means digger cuts through a cable or transmission line is brought down by bad weather. And there are majority that are kind of everyday occurrences. But as usual it's a little bit like car accidents. Car accidents happening every day and don't make the news. However, if there is, for example, plane crashing down, which happens every few years, then it's major news. Although the number of people killed, sorry for the comparison, in the plane crash is much smaller than the number of people killed every day or every year in car accidents. To some extent, this is the truth about power systems. So I'll be talking about a number of blackouts, which in the year 2003 was particularly good in blackouts, number of those happening all over the place. Then 2006 was not that good, it was only one, and I'll be talking about disturbance which happened in May 2008. But first, before I start talking about blackouts, I'll say a few words about how power systems are modeled, and this will to some extent refer to the discussions which we had in the previous presentation. So what you can see on the left is the map of transmission, high voltage transmission network in Great Britain, together with power stations. I don't think you can see power stations are kind of bigger colorful dots, while the lines are transmission lines. So basically it's a network. A network is a graph. So in terms of graph theory, it is a planar graph. It means very rarely we have lines intersecting each other. And we are talking about nodes and branches in electrical engineering. There are obviously buses and vertices and lines and edges in graph theory terms. Now, what's the size of the network? In this country, high voltage transmission network has about 800 nodes and about 1,200 branches, which is kind of medium-sized network. If you look at the continental, the UCT, UCT is old name for the Continental Network Organization. And also American networks, they consist of several thousands of nodes, because you can think about it as a number of those similar kind of graphs connected together. So it's a large-scale problem. Well, depends on what you mean by large-scale problems. Typically, those big continental networks will have several thousand of nodes, maybe 10, maybe 20,000 nodes. And now the question which was discussed in the previous presentation. For normal analysis, how, and for example, the blackouts analysis, which I'll present today, the network will be described by algebraic equations, which are basically first and second Kirchhoff's laws. Sum of the currents at any network node must be 0, and sum of the voltages around any closed loop must be equal to 0. And that sometimes causes problems with graph theorists who are used to transportation networks when only the first Kirchhoff's law is valid, while the second Kirchhoff's law not necessarily. Basically, current flows in electrical networks according to the physical laws. We cannot say, I want this amount, I can not force the network for this amount of current to flow that route and that amount of current to flow on the other route. The amount of current is fixed by electrical parameters of the network. So these were the algebraic equations. The presentation just before lunch dealt with differential equations. Differential equations are valid, are due to, as in the presentation before lunch, dealt with the synchronous operating of all the rotating generators. You have a number of generators in the system and are connected by electromagnetic forces. So if you disturb the balance of forces, or torques, because we are talking about rotational movements, you have some rotational movements of the generators with respect to each other, and this is described by differential equations. And those differential equations are usually they are described in a short time scale. It means in the time scale of seconds. If we are talking about voltage stability, which can also be a problem, we are talking about time scale less than a second. But for the analysis which I'll be talking about, you can understand blackouts talking only about algebraic equations. You can leave differential equations aside. So now in terms how we can prevent blackouts, how power systems are run. Well, I think it's obvious for everyone that we cannot live without electricity. Modern society cannot live without electricity, and it's only brought to mind to everyone when actually we do have a blackout and we realize you can't do anything about this. I mean, there are famous cases in the United States when there were rotating blackouts due to the problems of California, and then people couldn't leave their houses because all the doors were electrically operated. And they couldn't open, of course, the garage doors because they were all electrically operated. They couldn't even flush toilets because that was also electrically operated. So people are completely trapped, and they didn't realize it until it's happened. So we take security of supply for granted. We assume that when you flick the switch, the power is on. And so that means that power systems have to be designed and operated in a robust manner. So what does it mean, robust manner? It means in power system engineering, we call about credible disturbances. It means things which are likely to happen from time to time. And systems should ride through those credible disturbances without any intervention, without any problem. Nothing should happen. Now, what are the credible disturbances? It's always a trade-off between the cost and the benefit. The cost because you need to keep reserves. If you try to protect against everything, it will cost you a lot of money. But on the other hand, you have to you try to maintain certain security of the supply. So there is a trade-off between the two. So for proper, I mean, from the yes. So optimal solution, again, from mathematical point of view, would be some kind of probabilistic risk assessment, and I'll come back to it later. However, the practice since the beginning really of the electricity supply industry, it means over 100 years, is to use a deterministic criterion called n-1 contingency, which is a proxy for probabilistic risk assessment. What is this n-1? It means that, well, we assume that disturbances in power system are independent events, and they happen rarely, which means we should protect ourselves against a single disturbance occurring at any time, but probability of having two disturbances, it means lines going off or generators being tripped, is highly unlikely. And that has proved to be working quite nicely over the last years with a few exceptions. So we assume that it's highly unlikely that two or more units will be lost simultaneously. And that means that we should carry with the power operating reserve, generation reserve, such that the loss of single largest infeed, so-called infeed, it means generation, should be covered by other units which are connected in the system. In this country, the largest unit is a nuclear reactor at Sizewell B, and it's 1320 megawatts. It means at any time, if we lose Sizewell B, everything will be fine, because there's enough generation connected to the system to carry that reserve. And for the transmission reserve, we assume that in this country that the system should be able to cope with loss of a double circuit line, which is referred to as N-D, D for double circuit line, because those huge transmission towers, which you can see while driving on motorways, they typically will carry 2 transmission lines on one tower. And the reasoning behind this, if something happens to one of those towers, lightning strike or something like that, it may knock off operation both lines at the same time. So the question is, if it's working so well, so why do blackouts happen? And usually blackouts happen when N-1 contingency analysis has not been done properly, and that was the case with the Italian blackouts and the European blackouts in 2006. I'll be talking about them. Or when more than one thing went wrong, and that was a case with the American blackouts, the Sweden blackout, and there's a GB disturbance in 2000. So basically it was N-2 or N-3 event when more than one thing went wrong. Or sometimes you may have so-called hidden modes of failure, and that was a London blackout in 2003, about which I will not be talking about because that was not wide area blackout, it was just localized in London. But because it was in London, it was all over the press, obviously. There was a similar one in Birmingham, but no one has heard about it because it's Birmingham. Sorry if anyone is from Birmingham. Basically, due to some circumstances, basic settings of one of the protection equipment was wrong, and it came to line in unusual disturbances and then caused the tripping of a part of the network. So that was the traditional view. However, things are changing now, and at the end of the presentation, I'll be talking of this brave new world of renewables and smart grids. Again, there was some discussion this morning about it, and well, I'll talk to this point that those new circumstances of stochastic renewables and smart grids may require the use of probabilistic risk assessment. And I'll be talking more about this. Sorry, this is a little bit of the advertising of my tomorrow's lectures at 3:30 about mathematical modeling of future energy systems. Thursday. Wednesday. Wednesday. So it's tomorrow. Sorry, not Thursday. Tomorrow. Tomorrow, 3:30. So classification of blackouts. Well, again, when talking about blackouts, we talk about 2 types of things which may go wrong. Something may go wrong with the transmission system. It's not good enough, so we are talking about transmission inadequacy, which means that what we may have is a failure in the transmission network which causes a cascading overloading of the network, and I'll give you examples. So most of the blackouts I'll be talking about to them are this kind of blackouts. Or we can have generation inadequacy, where basically failures of power plants cause deficit of generation. And that was the case with the disturbance 2 years ago in this country. And usually we have actually a mix. It means there was some initial failures of transmission lines, they will knock off part of the network, cause separation, and then there'll be deficit or excess of generation in parts of the network. So the year 2003 were particularly exciting for me as a power engineer, because there was 2, 4, 6, 8 large blackouts, and it was all over about 2 months, 6 weeks period, so there was almost 1 blackout a week. And that was just great because newspapers rang me up, asked about interviews. I think Daniel sitting here was also in the same situation, so we are all in the very high demand, which is unusual for power engineers. So this could be summarized by this slide, which shows this guy who's suddenly surrounded by beautiful ladies at the cocktail party and finds himself to be center of interest, which had never ever happened to him before. Sadly, has not repeated anymore afterwards. Now with the global climate change and things, it's a little bit of that, but not as exciting as it used to be. So let's start from the overview of the blackouts. So the biggest of them all was in the United States. It was United States and Canada, and a couple of pictures which always people show when talking about them. So these are the lights over northeast coast of the United States just before the blackout, and this is the one after the blackout. As you can see, lights shaded, although not entirely. And this is not New York Marathon. This is people because the blackout happened at 4 o'clock in the afternoon, so the people were leaving work and walking through Brooklyn Bridge in New York. And the only lighted point in the New York was the Statue of Liberty, apart from some emergency lights in windows. So where did it happen? Again, I'll have to use our wonderful tool. So the area of the blackout started around Lake Erie, over here around Cleveland, which was the area operated by First Energy, and that was the area around it. Then it spread over a wider area. One important thing which I wanted to show you is that that area of the United States is managed by different colors, show different utilities which manage different areas. So one of the underlying reasons for the blackouts, for that particular blackout, and also for the blackouts in Europe, which I'll be talking about later, is the question that those utilities did not talk to each other as well as they should. So it's the question of communication, locational awareness, what's happening. And now how it all started? Well, it's very simple. Transmission lines are for transmitting power. It means there's a current flowing, and as we know from physics in primary school, when there's a current flowing through a conductor, the conductor gets heated, transmission losses, it gets heated, it extends itself, and in this particular case, so basically there should be clearance below them. In this particular case, the trees were not cut up, as they should, so that means when the line extended itself, it touched some of the transmission trees, so there was a short circuit and the line was disconnected. And there shouldn't be anything particular about this, because those things happen had an n-1 contingency condition been satisfied. Now it wasn't. And the reason it wasn't, it was, well, Americans say, well, it's a question of bad luck. Or was it bad luck? I'm not sure. The problem was that alarm and logging system in the First Energy, this is the local utility where it happened, control room failed 1 hour before the whole cascade started. And even worse, the failure system, the system failed, but the control engineers did not know about this. So on their screens, everything was fine, and suddenly they were getting phones from people saying, well, the lights are off, and they're saying, what are you talking about? You know, we see on our screens that everything is fine. So before they started to take action, there was some time, crucial time was lost. So when they did start to take action, it was too late. So basically, the condition was, the n-1 condition was not satisfied after a first few trips. And now, why do we have those wide area blackouts? Why do we have these cascading events happening? So this graph shows loading on number of transmission lines in that area. So over here, the first line tripped, and as you can see, when the first line tripped, the loading on other lines went up, because what you have, transmission network is meshed. So when you lose one of the transmission lines, then the power which was flowing that transmission line redistributes itself automatically, almost instantaneously, through other parallel lines. That means the loading went up. That caused overloading of another line. So that means so when that one tripped, it means the loading on other lines went up. That means that here that line got overloaded, so that it tripped, and etc. and etc. So you have a domino effect basically when lines tripping in turn. Voltage was mentioned before, voltage stability problems. Usually those blackouts are connected with voltage stability problems, because when you have increased loading on transmission lines because of the line tripping, according to the Ohm's law, the voltage drop on the other transmission lines increases, and because the voltage drops increases, it means the whole voltages in the whole area goes down. So you can see that graph shows the voltages on different transmission lines in the area, and after each of the line trip, the loading on the lines went up while the voltages went down. So that means voltages become depressed and then they started voltage stability problems. I have no time to talk about too details, but basically, as you can see at the end, there were some oscillations due to the voltage stability problems. So how the whole thing looked like? So this is the initial area of the blackout, and you can see the power was was flowing from the south around this area of Lake Erie. This is Canada to the north, and the arrows show how the power was supplied to different parts of the network. So when those trips started to separate that part of the network, the power started to flow in the around way, because there were trips over here. So that means that arrow became bigger compared to this one, because more power had to come through the existing transmission lines, which are still operating. Then those trips started to get affected larger area. It means that area which was supplied over here, the power had to flow in the around manner, and again was overloading more transmission lines. Then eventually that path was closed to the power which used to flow from the left. It means more power had to flow from the right to supply the same area. Then, of course, those paths started to be more overloaded. That means that power had to start to flow around. And now it got interesting, because those transmission corridors was cut, and now the power had to flow all around area through New York. Over here at the end we have New York. So New York, which is hundreds of miles away from the initial disturbance, suddenly was hit by this huge power flows. They didn't have idea where is it coming from. So eventually the whole area was disconnected over here, and we had a power blackout affecting northeast of the United States, including New York and parts of Canada. Interesting thing is the speed of propagation. As you can see, nothing was happening. So there was this initial line trips, but this is a number of lines in transformer tripping. So there is not so much happening, but when it starts to happening, in about 2 minutes it was over. So it is like an avalanche effect. Once it starts, there is no way you can stop it. So that was the big American blackout in 2003, and a couple of weeks later there was this blackout in Scandinavia, affecting western part of Denmark and Sweden. Eastern part of Denmark is connected to the rest of Europe, while the western part of Denmark is connected to Scandinavia. So the situation was, it was normal load, big margin, nothing should happen really. Denmark is self-sufficient, but this southern part of Sweden is supplied by big power stations which are located in the north. So basically power is flowing down those transmission lines. And then that power plant over here tripped due to some internal problems. So we lost one large power station. It's okay, N- contingency, no problem. The problem was that 5 minutes later, they will double fold the bus bar over here in that substation, and that tripped 4 transmission lines. That means that what we had over there was N-5 contingency, rather than typical N-1. That means the system was not designed to cope with such a problem. Another power station over here tripped, big power station, and there was a blackout in that part of the network. So that blackout really didn't cause much of the debate afterwards, because that was assumed, well, this is highly unlikely event. It was N-5. Well, it happens once every so many years. Unlike the American one, where they're still discussing who should pay the bills, basically. Another big one is this Italian blackout. This is the photo. It happened in the middle of the night, and you can see only the lights of the cars passing through Rome. This is the night view of Rome. And that also shows one thing, that people think, well, blackouts happen at the peak load when the system is really stressed. This one happened in the middle of the night, when actually the load is not that high. It is minimal, and yet there was this big blackout. Now, why it happened? Before I explain why it happened, I'll say something about frequency. I don't know, maybe I'm stealing something from Mark, who is going to talk later about frequency effect. So what is the mechanism, why frequency is important when analyzing what's happened to the generation demand balance in the power system? Well, it's obvious that power generated must be equal to power consumed, law of preservation of energy. And frequency is the same in any part of the network. I mean, people were asking over the break, how is it? Basically, within the whole interconnected AC network, because the electromagnetic forces which link synchronous generators, they cause them all to rotate at the same speed. That means the same speed, and speed means frequency. So the frequency is the same in any part of interconnected network. It means in this country, down in London, the frequency at any instant of time is the same as up in Scotland, but may be different than in the continent, because the British network and the continental network are connected by DC connection, which separates this frequency effect, because it's all based on frequency. And again, if you look at Europe, the frequency is the same in northern Germany and Poland as in Portugal, the other side of the continent. It is because all those generators kind of rotate together, and that can be visualized by this picture, that we can think about generators as this car which pull together one big wheel. This is the system load. So if basically that means that all the cars go with the same frequency, because then they go with the same speed and is the same frequency. So what happens now? What is the load frequency mechanism? It means what happens if you suddenly lose a generator. That means one of the strings snaps and we lose one of the cars. Well, of course, in this particular case, because the car is too big compared to the pulling force with all the cars, the whole system will slow down. Mechanical system. It is the same thing happens with generators. If we lose one generator, then energy required to supply the load will come from kinetic energy of all the other generators which are connected to the system. It means the frequency will drop. And as frequency drops, this is picked up by so-called turbine governors, which control generation of individual power stations, and they will pick up this signal of dropping frequency to automatically increase generation. So it is all automatic without human intervention, and this is how the system has been designed. So basically the whole system responds to any change of a real power balance in the system. And if frequency drops too much, for example, if we lose 2 or 3 cars at the same time and the remaining cars are too small to pull up the big wheel, then we have to activate load shedding. It means cutting off customers, because there is not enough generation in the system, and the only thing you can do is to reduce the demand. So in other words, if there is a generation deficit, the frequency is dropping. If there is generation surplus, the frequency is increasing. Sorry about this introduction, but I need it in order to explain what's happened with the Italian blackout and also about the British blackout, which happened in 2008. So this is Italy. Well, the northern part of Italy. Well, this is the rest of the Italian boot. And Italy is connected to the rest of Europe by a number of lines, which you can see over there. And now the situation, why blackouts happen at night? Well, Italy is a big importer of power, the biggest importer of power in Europe. Now, why is it? The reason is that in the 80s, there was a referendum which banned a construction of nuclear power plants. So they were not allowed to construct new nuclear power plants, and they didn't construct in other types of power plants. So basically, they ended up importing power from France. And guess what type of generation is dominant in France? Obviously, nuclear. So basically, it's a typical NIMBYs approach. And you cannot really do it in Europe because we are all live closely together. So the situation was that in the middle of the night, Italy was importing a quarter of its energy, mostly from France, but from other parts of the network as well. And that was about 300 megawatts more than agreed. All the countries in Europe agreed their schedule before time. It means they say, I will import so much from you and export so much from you, and etc. And they come to an agreement how it all will work. So Italians were 300 megawatts over the limit. Now Switzerland over there was operating close to N-1 security limit. However, they didn't know about this, and neither the Italians know about it, because again, it's in Europe, each country does N-1 analysis on their own. There is no overall Europe security assessment, and that was one of the causes of the problem. So what's happened is that one of the transmission lines in Switzerland, this is number 1, tripped. Again, touched a tree and tripped. Now, what's happened next is a still matter of dispute, because what the Swiss were saying, this is Etrans, which is Swiss utility. They said that informed the Italian utility what's happened. It means that the line tripped and etc. Italians were disputing that. They're saying that only they were told they're over the limit. And now, characteristic thing about again power system operation is, now this is 21st century communications and etc. And there are still no, they communicated by telephone, just by picking up telephone, and there are still there are no recordings. So basic communications by phone, by fax, and now take it with respect to the graph which I showed about speed of blackouts. I mean, it happens very quickly. So this is very much operation of power system in Europe. When you have those interconnected power system, is still somewhat behind what it should be. So what the Italian did, they reduced input by 300 megawatts as requested, but that was not enough, and 2 more lines tripped, two more Swiss lines tripped. There was cascaded tripping, the same mechanism as I've told you about when there was this American blackout, and in a few minutes, Italy lost synchronous with UCTE, with the rest of the Europe. That means they operated as an island, electrical island, that 20% deficit of generation, and that means when there was deficit of generation, that led to the frequency drop. So that graph, this is the frequency, what's happening to frequency, and this is scale on the left-hand side, and those lines show this is deficit of generation, and the scale is on the right-hand side. So for example, initially when Italy separated from Europe, there was about 46 gigawatt, sorry, wrong scale, 7 gigawatt deficit of generation. That's why frequency was dropping very quickly. Now, as frequency was dropping very quickly, then automatic load shedding was activated. So as you can see, they switched off also the pump. They had a lot of pumps, so they switched off the pumps. So basically, so as you can see over here, the deficit of generation was completely negated, and even they had surplus of generation. However, because of the dynamics of the problem, and because the frequency was already pretty low, below 48.5 hertz, they started to lose traditional power stations because the frequency was low, and every power station has different pumps, and those pumps depend on frequency. If frequency is too low, the pumps drop, and you have basically positive feedback mechanism. So as you can see, they started to lose even more generation. The frequency was going down, 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 until eventually it reached 47 hertz. And when it reached 47 hertz, basically 47.5 hertz, everything stopped. All the power stations stopped to produce, and there was a total blackout. So it took only 2.5 minutes. And now we have interesting thing. So there was a 2 blackouts in 2003. I didn't talk about others because there's not enough time. This one is very interesting. It happened in 2006. This is called UCTE. UCTE is Union for the Coordination of Transmission of Electricity. Basically, it's Association of Transmission System Operators in Europe. Now they renamed themselves ENTSO-E, European Network of Transmission System Operators. The initial disturbance was, and that shows you the dangers of interconnection. I mean, interconnection is great. It brings enormous benefits in every day of operation. However, it causes problems when things go wrong. The initial disturbance was in northern Germany, but you had customers affected when it spread in Madrid, to Portugal, and in Spain. So what happened? The situation just before the disturbance, by the way, the UCT talks about disturbance. They don't use the word blackout because doesn't sound nice, so they talk about disturbance because it wasn't a total disconnection. So you have those 3 parts. Basically, the western part of Europe was importing nearly 10 gigawatt from the eastern part of Europe. including there's a lot of wind. It's quite important over here because wind starts to come into picture, about 5.5%. And there was strong those east-west flows because there was a strong wind generation in northern Germany, and it caused problems, as I will show you later on. So what happened? Basically, that guy did it, sort of. This is a ship. So what's happened was, this is actually quite normal event, because there was this ship had to pass the river, and the transmission lines which are hanging along, above the river were too close to the ship. So this was the shipyard requested a disconnection of a transmission line. This is a routine event. Nothing should have happened. Now something did happen. Why is that? Well, initially this disconnection was supposed to happen on the 5th of November 2006. However, on the 3rd of November, the shipyard requested bringing forward this connection by 3 hours. And that affected all those coordination of imports and exports in Europe I've told you about. And it was because it was just 3 hours, so there was no time to modify all those schedules. So so what the E.ON, which is the American utility which runs the area, what they should have done was they should have redone the contingency analysis, N-1 contingency analysis, to check that the situation is safe. However, they assumed, based on their experience, that the system is secure, even in that situation, despite stronger winds. And unfortunately, they've proved to be wrong. So at 9:30, E.ON switches off the line. And half an hour later, there were alarms that the flows in the areas are too high, and then E.ON decided again, without doing proper analysis, that they have to decouple a busbar. This is electrical connection, basically changing slightly configuration of the network, in the hope that they should reduce the current. It did the opposite. The current increased. And basically, because the system was not N-1 secure, because they hadn't done the proper N-1 security analysis, there was a cascading tripping. So the line started to trip over the whole Europe, and the UCT is separated into 3 regions with different frequencies. So you have the western part, which was the net importer, because there was net importer, so they had 8.9 gigawatt deficit. So this is equivalent about 6-7 large power stations. So they ended up, because there was a deficit of generation, this frequency went down to 49 hertz. In the eastern part of Europe, which was exporter of about 10 gigawatts, because there was too much power, so they ended up with a too high frequency, 51.4 hertz. And the southeastern part of Europe, there was just slight deficit, 0.8 gigawatt, which is not much, is below 1 power station. So that's the frequency dropped to just slightly below 50 hertz. So there was not much happening. So the main problem was in Western Europe, how to maintain security of supply with such a huge deficit of generation, and how to contain things going wrong in the Eastern Europe, because there was too much generation. So in Western Europe, with this deficit, according to the mechanism I've told you about, the frequency dropped to 49 hertz. That triggered automatic and manual load shedding, about 17 gigawatts, and tripping of pumped storage units, which is what it should happen. So it did work. However, the problem was that also the frequency dropped caused 10.7 loss of 10.7 gigawatts of generation. So it means more load had to be shed. Now, what is interesting is that that there's a DC connection between France and this country, and usually because power in France is cheaper, because they have nuclear power station, that tends to operate in export mode to Britain. So at that time, they were exporting about 2 gigawatts to Britain. They had a huge deficit of power in France, and yet they still kept exporting, because that shows you how DC connection isolates the network, so you can do independent thing in both of them. Of course, they should have tripped it. I don't know why they didn't. I don't know, maybe contracts were such a severe, or so, I don't know, maybe they have noticed, I don't know. But that shows you how DC connection separates electrical networks. Yes? Sorry?
They would have brought down the UK, that's not the answer?
They would.
If they'd have knocked off 2K to the UK?
Well, that would have problems, but you know, UK has to be connected, it has to be n-1 secure as well. It means the assumption is, I think they assumed that they could have dropped one line, because this DC connection consists of two lines, and each of them carries 1 gigawatt, so they could have dropped one of them, but couldn't drop two because they would have caused problem in the UK. So here you have graphs of frequency with time in all three parts of the network. So this is east, this is southeast, and this is west with the low frequency, number of resynchronization events, and eventually they managed to resynchronize the system. It means the frequency was back the same in all parts of the system at about 50 hertz after half an hour. And now the last of the events I wanted to tell you about. This is in GB in May 2008. And this is what they refer to as 2008 event. It was a near miss. We nearly lost it all, but we didn't, which is quite good. But it was actually quite close. So what is the situation? In the graph you can see basically what happened to the frequency. They refer to the loss of generator A and B, because this is from the official National Grid reports. However, well, everyone knows that generator A is Cockenzie in Scotland, and generator B, Sizewell B, in England, a big nuclear generator. And that was n-2 event, completely unconnected, independent event for unconnected reasons. First, Cockenzie tripped. This is a coal-powered power station in Scotland, and then Sizewell B. And they lost within 2 minutes. So you can see here first Cockenzie dropped, and there's a slight drop in frequency because Cockenzie is small, it's 345 megawatts, and then huge drop in frequency due to dropping of Sizewell B. Sizewell B is nearly 1300 megawatts. So we were down over here, and initially we lost 1700 megawatts, over 700 megawatts. Now, remember, I've told you that the system is designed to be n-1 secure, and this n-1 means Sizewell B, then it is secure against the loss of 1320 megawatts. More than that was lost. That means we were bound to have some problems, and the situation was made even worse, that due to the dropping frequency, there was nearly 300 megawatts of wind tripped, or low frequency. There's a long story about it, but basically wind generators are sensitive to frequency, and if the frequency goes too low, they trip. So nearly 300 megawatts of wind tripped, and this is this third drop over here of frequency up to over here. So you can see drop of frequency from 50 hertz to 48.8 hertz, and the total nearly 2 gigawatts lost. That caused automatic load shedding. It means customers were disconnected automatically a different part of the system, over 500 megawatts. And additionally, National Grid reduced voltage. If you reduce the voltage, then the power demand goes down, because there's a lot of load which the power demand depends on voltage, like for example heating loads. And that brought about 1200 megawatts. And so more generation was connected, and they've managed to restore the supply. As you can see, the graph is going up. So there was a near miss, but actually when I talked to National Grid people, they are saying we were pretty close to a total blackout. There was no much left. They just got away with it pretty tightly. So that was the overview of the blackouts, and now let's talk about two things people are always interested in, they're always asking me. First is, will there be more blackouts? And what's the outlook for the future with all those brave new worlds of renewable generation and smart grids? So, well, will there be more blackouts? Well, one good thing about blackouts is that people learn from mistakes in the past, so the people learn from blackouts. However, there's a famous saying is that the generals are always prepared to fight the last war, not the future war. And I'm afraid there's a little bit of that in what we have. So there were certain lessons learned from the blackouts, and especially in terms of coordination and collaboration in Europe and United States. I've told about those problems that those utilities don't really talk to each other, and they don't know what the neighbors are doing. However, there are new problems which we have, and some of those problems were touched upon in the discussion in the previous session. So some of the problems. First problem is generation adequacy problem. And that was Ofgem published so-called discovery report last year, which was quite interesting. They presented that they have identified a number of threats to these countries and ways which we can do to avoid them. And one of the problems is that we may have serious problems with generators after 2015. And this graph shows different actions which have to be taken in order to avoid those problems to occur. For example, there is the European LCPD, Large Combustion Power Directive, which means that coal-fired power plants have only certain amounts of hours they can operate. And if that is not relaxed, a number of coal power stations will have to close in this country. The top two graphs refer to gas, all the problems with gas supplies to this country, and northeast gas running out. Big question, obviously, with nuclear. We don't know. It's a political question, whether we'll have more nuclear or not, and whether there'll be enough. There's a number of scenarios, and people always assume, oh, we'll have so much wind, and etc. But we don't know whether it will happen or not. So basically, it's a political issue. There's regulatory uncertainty surrounding. That's why people are not building enough power stations, and it's a big problem. However, this is mostly political problem, so I will not talk about that because politics is really difficult to model by mathematicians. Maybe people have tried, but didn't come to good results. Some of the things which are interesting, which are causing problems, and which can be modeled by mathematicians, is one of the problems which was mentioned in the discussion in the morning, which is about increased penetration of renewable generation. As I have showed you, wind was already a contributing factor to the European blackout in 2003, disturbance in 2003, and the disturbance in this country in 2008. But that was due to mostly to the frequency, because the wind generators were sensitive to frequency. That can be fixed, because it is a question of designing appropriate protection for those wind generators. However, this is a big thing. If we are talking about the future, now the government is committed to 80% reduction of CO2 by 2050, and Climate Change Committee reckons that will require total decarbonization of electricity generation by 2030. And this is a very scary prospect. Total decarbonization, it means everything. There should be no gas, no coal, unless it is with carbon capture and storage. And, well, one of those graphs which everyone shows when wind is concerned, what will happen if everything relies on wind, and wind does something like it did, for example, in 2006. This is a graph showing wind generation over a couple of winter months in this country. As you can see, wind generation can go all over the place from day to day. And so there is a huge uncertainty regarding what will be the actual generation. So one problem, of course, which may cause problem with power system operation and causing blackouts is renewable generation, increased uncertainty. And the kind of mirror image to this one, which may help or which may things worse, is this issue of smart grids. Well, people are always talking about smart grids, but there's been a lot of discussion what those smart grids really are, and we've had a number of discussions in the power engineering community. But, well, this is a picture from this European, one of the European platform or consortia which produced that. Basically, the idea is that everything is singing and dancing. We have comms-enabled responsive demand. So it means basically people have solar panels, micro CHP, There is a wind all over the place, all the buildings, everyone has some smart meters, so it all will enable responsive demand. On top of that, we'll have electric cars, so people will charge and discharge whenever national grid demands, which is very doubtful. So basically, what we will have highly stochastic generation and highly stochastic demand. And what I suspect and believe is that the traditional way of running power system, it means with n-1 contingency criteria, may become obsolete soon. So probably what we will require is a new probabilistic risk assessment tools, both for operation and planning. Well, there's discussion about planning, but certainly we'll need probabilistic risk assessment for operation. And I'll be talking more about it once again tomorrow when talking about modeling challenges. But this area is very much for mathematicians, because this is where mathematicians' input is required to understand what's happening and understanding how to run the system in the optimal way to overcome blackouts. And there is one interesting thing, is that a new mode of failure may appear, because that smart grids concept depends on the comms. What will happen when the comms fail? So there's a new possible mode of failure, which is not failure in the transmission network, power system itself, but if something happens to the communication network, which it may, this may affect operation of the power system because they become interconnected. So a new mode of failure which has not been looked at all. So, and the last thing I wanted to talk about, just to leave some time to discussion, this is an example. Now, Stan in his kind introduction mentioned my interest of long-time interest in working with economists, with mathematicians, doing interdisciplinary research. And this is a project which we've started recently. We got an EPSRC grant, started January, and it was from Complexity Science Corp. And this is collaboration between mathematicians and power engineers. So we have people, graph theorists from Southampton, operational research experts from Edinburgh, and there are some around here in this audience today, and power engineers from Durham, it was myself and another guy, Phil Taylor. And what we want to do is look at the preventive network splitting. So the idea is like those blackouts which I showed you, with the American blackout or the European blackouts, what we have at the end of after all that process started is a separation of the network. But that separation is, no one really knows how the network will divide itself. And the end result is the large number, millions of people are being blacked out. So what we are trying to do is just look how to prevent it happening, and basically split the network in a controlled manner into islands, and in this way, first of all, to minimize the number of people disconnected, and secondly, making reconnections more possible. I think that this is really exciting project, but one of the problems, I think the main problem, is something which actually you could witness in the session before the lunch. It was the question of communication us. Basically, power engineering talking to mathematicians and mathematicians talking to power engineers. We need to establish common language and understanding of the problems, because we talk to each other, but we don't understand each other. And the education, the mutual education, is a must, and it's very difficult. And actually, this particular project we started with a number of seminars when each group in turns gives presentation trying to give a very simplified idiot's guide to problems, so the other side understands. It doesn't mean that they think the others are idiots, but just it means that some doing something in a simple language that people from other disciplines understand what's happening. So conclusions. N-1 contingency served us well over the last 100 years. However, we did have a number of wide area blackouts, which I've been talking about. We certainly do face new challenges of increased wind penetration and smart grids, which will make things more interesting And I'm very much convinced that we do need very strong mathematical input in order to deal with all those challenges ahead. We power engineers, I don't believe we are able to solve those problems on our own. Thank you.
Thank you very much. We've got quite a little bit of time for questions on that.
One lesson to take home from your talk is that a big factor in the spread of blackouts has been large generators tripping due to low frequency. And I'm wondering if the power plant designers haven't put any thought into making them more robust to low frequency, so they don't trip until 40 hertz instead of 49.7 hertz.
40 hertz would be difficult, but there's an interesting example again from Ireland, and Mark can correct me if I'm wrong. Ireland is a small country, which means that all the disturbances are, you can see immediately in frequency. Because in Europe, it's a big country, so if you lose one power station, nothing will happen. In Ireland, because you have just a few power stations, if you lose one of them, percentage-wise, it's a huge loss. It means the frequency goes all over the place. And I remember Mark invited me to a seminar, and there was a guy from Airgrid, and he said that he was worried because after connection of Northern Ireland to the South Island, the system became more stable. And before they had frequency excursions all over the place, and they were able to check that everything works down to 48 hertz or whatever is the limit. But now, because everything is nice and stable, they don't know if it would work. So one problem is that in Europe and in this country, because frequency is kept pretty tightly, we don't really know what's happening when you go to frequencies 48 hertz, 47 hertz. There's a technical problem. If we could go to 40 hertz, that would require huge changes in the design of all the pumps which run power stations. Because there are all kinds of problems. Theoretically, probably it could be done, but the cost of that would be huge.
The cost of blackouts is also very huge, so are they really doing the right cost-benefit analysis?
The question of cost-benefits analysis is important. Basically, after each of the blackouts, immediately chief executives are on the main news, people are going up in arms, but after a few weeks they forget about it. Remember, if you want to prevent a blackout, that means you have to, like this I mentioned initially, there's a cost-benefit analysis. And you have to run huge reserve, and that costs a lot of money, and it's 24/7, it's all the time. The same question of redesigning all the power stations, the cost of that would be astronomical. So there's a question, let's take another example, completely different example. When I went to India, sitting in the restaurant, and suddenly lights went off, and air conditioning went off. And no one really paid any attention, because after 1 minute, you could hear boo, 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 and generator started in the background, and the power was back on. So this is a bit extreme example, but basically the view has been that it's better to accept a blackout every 10 years, 20 years, rather than the current huge cost of preventing that things happening here in Iran. It's like with snow in this country. We had the strongest, the harshest winter for 30 years. And again, people were saying, oh, why don't we have this fleet of, this winter every year in Europe, and they managed. And here, the country was brought to a standstill. But then there's a question of cost-benefit analysis. Should we pay for 30 years just to prevent this one winter? So it's a difficult question.
Right.
Could I just ask a question about the role of frequency and voltage in communication and adaptation? So if I understood correctly, that the frequency is varying is a signal that could be perceived by anywhere in the network that there's a mismatch between supply and demand and the direction of it. If I understood correctly, there isn't any adaptation there, whereas with voltage there is. That if the voltage differs, then that will actually supply less power. Because of reactive resistances will have less power dissipation if the voltage has gone down, presumably.
Well, there are voltage regulators as well. I didn't mention about it. Well, the voltage regulators was actually the presentation before the lunch was about voltage regulators, which designed in a similar manner to keep the voltage stable in the system. Of course, within the capabilities of power station, of its so-called exciter. So the voltage is kept constant through the feedback mechanism. When the voltage drops down, the generator has the voltage controller, which tries to keep up the voltage up to the level until it hits a limit, and then that's it. It cannot keep it anymore.
I see. So that's sort of really backup. I mean, a sort of.
No, that kind of two independent control loops.
So for frequency, if the frequency drops, then what are the energy consequences of that? The frequency, the inertia of the, if I've understood it correctly, the inertia of the physical turbines is being used there to that's why the frequency is dropping with some time constant. But does that of itself produce less energy supply to consumers?
Oh yeah, well there is effect. Well, there is effect that you are talking about that the loads use less energy. Yes, there is, but it's much smaller effect. It's an order of magnitude smaller. It means when frequency drops, you can think about fans, for example. When the frequency drops, the fans start to rotate slower. It means they take less power from the grid. So there is response of loads, which helps, but that effect is an order of magnitude smaller. So it does help a little bit, but not much.
Daniel.
Janusz, I agree with most of what you said. Just a little quibble. I think in your your list of blackouts, you had two that were really bad luck, which was the Swedish one and then the British one. I think in all the other cases, you had a problem of communication in one form or another. And I think that's that's the same thing as you're talking about smart grid. I think the problem is already there. It's studying how communication in the system affects the fact that you're going to get a blackout.
Oh yeah,
It's a really interesting problem.
Oh, very much so. I mentioned it in passing, but didn't dwell on this, that you have all those utilities which talk to each other or which don't talk to each other in the case of Europe and United States. And they should be talking. But the reason they don't collaborate, it's not technical reason, it's not comms as such, because they could. It's a political reasons. Basically, that means that, for example, in Europe, we are working on a project with people like Carsten Neuhoff, who some of you may know, and a number of universities in Europe. We are trying to establish benefits from moving dispatch based on country by country basis to one generation dispatch, moving the whole Europe would be dispatched together. And there will be huge cost benefits of that, but that would mean giving up independence by the individual utilities over the all control areas. And basically, for political reasons, they are not going to give it. I mean, just look at the discussions we have in Europe about giving up power to Brussels. This is to some extent similar thing. So it's a question of so this is a political problem again. It's not a technical problem. That could have been done no problem with current technology. It's a technical problem. There is this so-called Florence Forum. You know about this, which basically there's a forum every year in Florence. Representatives of all the system operators in Europe gather together, try to solve those problems. And guess what is the result? Very little, because of the inertia and because it has to be consensus. Everyone has to agree with that, and that the progress is very, very slow indeed. But you're right, it's a huge problem.
So you were talking about the need for probabilistic analysis with more renewables and smart grid. I'm not criticizing that, but just a question really. Why couldn't you just have a more severe deterministic criteria like n-2 or n-3 instead?
And just a cost? Yes, of course you could. That's the question, again, is a question of a trade-off. So one thing you could have is n-2, and to some extent Britain has n-d, which is double-fold, which is more stringent than most of the countries in the world, which have just n-1. And from time to time, this exercise has been attempted. In National Grid, I think about 10 years ago, I think they considered moving to n-2. And they have come to the conclusion that basically the improvement of security would not be as high because the cost would be too high compared to the increase in security. They also look at the probabilistic risk assessment, and at that time, that was about 10 years ago, again they came to the conclusion that it doesn't pay off. But the situation is changing because of the intermittent generation, because of the stochastic demand as well. So we are talking, so if we just run n-2, the cost of that would be high. If we do something cleverer, more clever, kind of just-in-time delivery, again, I'll be talking about it tomorrow, there will be stochastic, of course, risk. So the question of getting the risks right, so the risk is not increased by using those other techniques.
But the disadvantage of using probabilistic methods is they're harder to understand by operators.
Of course. And that's why we need you guys over here to help us. That's why mathematicians are needed.
Comment over there from one of the operators.
Surely the other thing about the advantage of the probabilistic approach over the n-1 contingency or n-2 contingency is that when you've got lots of wind generation, lots of, say, small wind farms, it just doesn't fit into this n-1, n-2 category.
Yeah.
If you have, as we did in '87, a sudden hurricane, and we lose a huge swathe of wind generation because the wind is just blowing too fast, you could lose I don't know, 50% of your wind generation in how quickly did that hurricane come up? Half an hour? And that just does not fit into this n-1 contingency, n- whatever you want contingency pattern.
The granularity of the problem gets smaller, basically. That's the thing. So when the granularity of the problem gets smaller, you cannot use n-1 on n-2.
Yes, but what you could do, for example, if you have a 1300 megawatts reserve requirement to cover the loss of Sizewell B, you could have another 500 megawatts to cover the loss of a significant portion of wind. So you can have 1800 megawatt reserve requirement.
But it will cost you money.
It will cost money, of course.
Yeah, so that's what I'm saying. That's why you need some means of the cost-benefit analysis, which is better. Maybe n- increasing reserve will cost money. And National Grid did those kind of calculations. You can look at their report on system operation in 2020. They actually did calculate how much more will it cost to in terms of reserve to integrate all the wind on the system.
Chris,
Yeah, just another comment following on from the last two. One big difference between these issues Janusz has been talking about with conventional plant, where you really can lose 1300 megawatts of Sizewell instantaneously. When you get big losses of wind generation, it usually happens rather more gradually, and to some greater or lesser extent, you know it's coming when you get a really big decrease in wind output. So that the timescales on which you have to be able to handle these issues and the degree of foresight you have is really fundamentally different for losses of wind in feed and possible conventional in feed.
I just comment. You mentioned that wind had something to do with the 2003 event, Yanis. But my understanding was that it only had something to do with it as the system started to come back up, wasn't it?
2006, you mean European?
Yeah, sorry. That it only impacted the system when it was starting to come back up. It didn't have anything to do with the actual event. Is that not correct?
Well, it was both. Well, I didn't talk in details. It caused actually problems in both ways. So first of all, the wind farms started to get disconnected when the frequency dropped. But when the frequency started to increase, the wind started to be connected again, and that caused again disturbance. So it went both directions.
Yeah, but I think people need to understand why that happened. First of all, they dropped out because they were supposed to. That was their, they were within their requirements. And on the way back up, what happened was because they weren't being monitored. They were coming up back on, and the frequency was actually going up too high. And then my next question is about your project, about the last project you described. And I come back to my point this morning. You could deliberately split the grid into many parts for security reasons. Did they not try that in EDF?
Yes, they have a scheme, but it's a fixed scheme, which basically means if they have a number of monitors, and if they discover that something is going wrong, they have predetermined logic which splits the system in number of parts.
Yeah.
What we want to do, we want to use wide area measurement systems, which measure what's happening in the system all the time and do it dynamically, adjusting to the situation which you have at hand. So it's measurement based.
Do you think any CEO is going to actually agree to that? Because I think if I was the CEO, right, I'd say here's Yanis and the boys, and that's very interesting. But if I agree to this and it goes terribly wrong, because you have to realize that what you're doing could actually backfire completely and make matters worse, or will I just leave it, and if it gets bad, sure, well, at least I didn't do anything, hands of God.
So I think you'll have a big problem getting the CEOs to agree.
That's exactly what happened with the EDF system.
Yeah, I know that,
They
yeah.
calculated that the probability of malfunction was higher.
Higher, that's
than the
right.
probability of
Yeah.
it working
Blackout.
properly.
Yeah.
So they said they never put it into
Right, yeah.
Just like to say that an N-1 system is a probabilistic risk assessment. It just so happens that most of your variables cancelled out, and N-1 was a really good approximation to a very complex risk assessment. Similarly, analogous to what we saw this morning, where your reserve capacity comes about as a fixed margin because all your other variables have dropped out, and traditionally we've used two tools for energy security, which is N-1 and capacity credit. And both of these, as you said, are tools for the last war. And they don't help us understand common modes of failure or common modes of variability, as we see with large wind systems. But there are other common modes of failure in the gas system. For example, if gas imports get cut off, we just don't happen to model those common modes of failure very well. In our new probabilistic risk assessment tools, which I don't really want to abbreviate to NUPRAT, but it's handy. Under NUPRAT, we will be modelling these common modes of failure across wind, for example. And actually, they're easier to understand than common modes of failure across gas or uranium imports, because we actually have probability distribution functions for them, whereas we don't have PDFs for the Russians cutting off gas supply.
Yeah, well, both last points are really related to politics. And as I said, politics is very difficult to model. So maybe there's a challenge for the next workshop, organized by the Newton Institute.
That'll be a big challenge. Make a quick comment. I mean, I'm a great speaker over there. The N-1 criterion is the solution to the probabilistic risk assessment problem in the case where you've just got these discrete events that can happen. The generator's there, or it's not. And now if we move to a world in which there's much more variability, wind variability and so on, you have to do something that involves a bit more calculation. You're still going to see those those discrete events coming up in your answers. Probably, to a first approximation, what you would do is take the various N-1 scenarios and do a probabilistic assessment for each of them, because that's the way you do the probabilistic calculation. So it's not an either or, it's just going to be something more refined. It's going to be necessary in the future.
Yeah, just following on from that, the wind generation doesn't. That's my previous comment. Wind generation doesn't really increase the amount of primary, reserve, or response, whichever terminology you use, that deals with these very sudden events. But it does increase its wind generation increases the amount of secondary or replacement reserve which you need to have standing by to ramp up in case of more gradual deviations from forecasts.
Mark, again.
Just a point of clarification, Chris. While 18 months ago I would agree with your statement, I'm afraid I don't agree anymore. I think that some of the penetration levels we're talking about, and some of the instantaneous penetration levels we're talking about, and some of the events that could happen actually lead to a situation where wind, when it obeys the grid code, i.e. does exactly what we've asked it to do, can actually cause a larger contingency. Because if you do fault ride-through with voltage problems on a system where all the wind is on one side of the system, you get a situation where the voltage dips, and the amount of energy that's sucked out of the system during the fault ride-through requirement of the wind turbine, i.e. doing exactly what it was supposed to do, the total amount of energy sucked out can be greater than the largest contingency. And I can show you that, and in fact those results will be made public in about 3 weeks. So, 18 months ago, I would have said Chris is dead right, but it turns out that there's some other issues there that may end up in a situation where wind could be the largest contingency.
Is that a result of the grid codes being designed to fight the last war rather than the next war?
No, well, the grid code was, I suppose the grid codes came about because when wind was connected first, we didn't care what they did. That's what's happened in Europe, yes, right? So we just wind there, what the hell. Then we decided we better make them do something. But we thought about 10% penetration, 15%, but now we're going to 20, 30, 40%. we're a bit behind the times. But it only really applies in places like Ireland will be one of the places that'll see it first. Actually, what I'll do is I'll put a slide about that in my deck for tomorrow morning. But and I'm not saying it will happen, and I'll show you the slide tomorrow. It is possible that wind could be our largest contingency because it's obeying the fault ride-through requirements of a voltage dip.
Okay. Any further questions? Certainly, Jens, you stimulated a lot of discussion as well, and thank you again for a very interesting talk.
Discussion.